Hi, and thanks for watching. This video is about the derivation of the quotient rule, and the main goal of this video is to derive the quotient rule for finding derivatives from the limit definition of the derivative. So first of all, let's take a look at a function, and we're going to call this function f of x. Now, our function f of x happens to be the quotient of two other functions in terms of x. We're going to call those functions u of x and v of x. Now, oftentimes when we abbreviate things, we leave out the function notation. So you'll often see this written as f of u divided by v. And then the quotient rule is, and we have a nice little song for that, the quotient rule tells us that the derivative of f of u divided by v is low d high minus high d low all over low squared. All right, what that means is the lower function, low v, times d high, which is the derivative of the higher function, minus high d low, so the numerator times the derivative of the denominator. So now we have our low d high minus high d low all over low squared. Okay, this is the quotient rule. We use the quotient rule all the time, often without thinking about where it comes from. So what we're going to talk about today is where the quotient rule actually comes from. And in order to do that, we're going to talk about the limit definition of the derivative. So we're actually going to derive it from the limit definition of the derivative. So let me remind you what that limit definition of the derivative is. So this is the limit definition of the derivative, and remember, it's really just a slope as the gap between the 2 points connecting the secant line forming the slope gets smaller and smaller. So here's our y sub 2 minus our y sub 1 over x sub 2 minus x sub 1, and in general, since x minus x is 0, we usually don't write that. We usually just leave the h there, but it's important to remember that it's actually a slope calculation. So now what we need to do with this limit definition of the derivative is take our original function, which is right up here. It's the quotient of two other functions written in terms of x, and we need to plug it through this derivative machine. All right, so let's get started. When you do this, we first should probably calculate what f of x plus h is, so let's just kind of isolate this. And if we look at what f of x plus h is in terms of our quotient, that's going to be this. So you can see that all I've done is I've plugged in x plus h where I used to have x's. And then we also need an f of x. And so if I plug in x where I have x's, f of x is just going to be u of x over v of x. Okay, so now I can plug these two things into my numerator, and what happens to my derivative is it starts to take on the form of the u's and the v's. So we're starting to replace all of these f's with u's and v's. So our derivative, f prime of x, is going to equal the limit as h approaches 0, and now let's do our substitution. All right, I've substituted everything in. That's pretty awful. In fact, you're thinking, how is that any better? Well, I don't know that it is, but let's actually try to apply this limit. So this is telling us to let all the h's go to 0. If we do that, this is going to be u of x, if the h turns into 0, over v of x. So we're going to have u of x over v of x minus u of x over v of x. So that makes the numerator equal to 0, and the denominator, h is going to go to 0, is also going to be 0, and we've talked about this is not good, this is bad, so we can't leave it like that. We have to monkey with this a little bit more. Well, in the past when we've had limits with complex fractions, which are fractions nested inside of fractions, what we've done is we've found common denominators of the numerators and then written everything as one fraction that's not complex. So let's go ahead and do that. If you look at this denominator does not have a factor v of x. So let's put that factor in. And this denominator does not have the factor v of x plus h. So let's go ahead and multiply this side times v of x plus h in the numerator and the denominator. All right, so now what I can do is I can write my numerator as one fraction. I'm going to go ahead and do that. So my numerator is now simplified. It's one fraction, and instead of dividing, I can multiply by the reciprocal. So I'm going to multiply by the reciprocal of the denominator. I'm going to put my limit back in over here, and I'm going to see if that helps anything. Well, let's see. Let's let h go to 0. So if h goes to 0, the entire denominator is going to turn into 0 because we have to multiply by 0 here. And in the numerator, if the h went to 0, this would turn into u of x. So I'd have v of x times u of x minus u of x times, and this would turn into v of x, and that would give me 0 over 0 again. All right, so here's where a little trick comes in. What we need to do is we need to add v of x times u of x, and then subtract exactly the same thing, v of x times u of x, because that's going to give us a net value of 0, but we're going to add this and subtract it to the numerator so that we can do some fancy stuff. So let's try that. Now it does matter where you put each piece. You should put the addition piece right here. So we're going to put that after this last term, and we're going to put the subtraction piece right here. So give me a minute, let me rewrite all that, and I'm going to have a huge expression down here. So I've got that all cleaned up and written. It was a little bit painful, it was a lot to write, but I think we've got it. So now, if you look at the first two terms, what we're going to do is we're going to group these first two terms, and we're going to look for any common multiples that we can factor out. And if you look for common multiples, you see there's a v of x here, and there's a v of x here. So we are going to factor out v of x from these first two terms. Now, if you look at the last two terms, we have to be careful. We have to make sure that we change this to adding a negative, because if we want to group these, we have to make sure that we assign that negative sign to the first term. And if we look for common terms, we have a negative u of x here, and we're going to factor out a negative u of x here as well. So it's important that we grab that negative sign. And again, I'm going to regroup a few things, and I'm also going to yank this out in front, and I'm going to clean all that up, and then we're going to do some more monkey business. So far everything that I'm doing right now is Algebra 1, but the rearranging part are little tricks that you have to know in order for this to work out. So give me a minute, let me clean all that up, and then we'll look at it again. All right, here we go again. I've got everything cleaned up. And you can see here I took this denominator and I separated it from the fraction. So I just wrote this out in front. We still have v of x times v of x plus h times h in the denominator, so that doesn't change. And in the numerator, I factored out the v of x here and the negative u of x here. Remember, if you multiply this back in, your negative times your negative is going to get you your positive here. So that's okay. Now I'm going to do one other thing. I'm going to take and make sure all this stuff stays together as a product, and instead of dividing everything by h, since we can distribute division, I'm going to divide each term separately by h. So I'm going to take this whole term and divide by h, and I'm going to take this whole term and divide by h. And if you think back to the video that I did on deriving the product rule, this should look familiar, as should this piece. And if we apply this limit separately to this piece and this piece, what each of these become is u prime of x, and this becomes v prime of x because of the limit definition of derivative. So let's turn these into u prime of x, turn this into v prime of x, but remember we still need to apply this limit to all of the other pieces. So again, let me clean it up, we'll get back to it, and we'll talk about it in just a second. Okay, so once again, I've cleaned everything up. This u prime of x is now right here, this v prime of x is right here, and what I've done with this limit as h approaches 0 is I've made sure to apply it to each piece that hadn't yet gotten it, which if you look back here, this part needed the limit, this part still needed the limit, and this piece still needed the limit. So I've written those in 3 separate places, and that is completely legal according to the way you can manipulate the limits. So if we look at this, as h goes to 0, this is just going to become v of x. So I end up with 1 over v of x times v of x. And another way we could write that is 1 over v of x, that entire quantity squared. All right, then I've got times all of this stuff, which if you look at this, there's no h in this term, so this is just going to end up being v of x times u prime of x. And again, right here in this, when I take the limit as h approaches 0, there is no h, so that's just going to be u of x times v prime of x. And again, if I clean everything up and now I distribute my denominators, so my denominator here is officially 1. If I multiply these two denominators and multiply these two denominators, what you're going to see happen, sorry about that, is everything starts to get cleaned up very nicely. So 1 times this numerator is going to be v of x times u prime of x minus u of x times v prime of x all over v of x quantity squared. And if you think back to our quotient rule, what we have is low d high minus high d low all over low squared. So this is the derivative of x as long as x is written in terms of two functions u and v that are also in terms of x. So I can rewrite it like this, u of x over v of x, and we've got it. Woohoo! Also, I love golden retrievers, and I have one, and his name is not going to be revealed quite yet. You're going to have to watch more videos for that.